In this video, we will discuss about collision theory and the concept of activation energy, activated complex, and transition state. And also we will discuss how is it the reaction rates related to temperature and the energy diagram, which is also called Maxwell-Boltzmann distribution curve, and reaction mechanism. According to collision theory, for a reaction to happen, there must be collision between the reactant molecules. But not all collisions will result in the reaction and giving products. So for a reaction to happen, two things must occur. That means the molecule must collide with the appropriate orientation for a reaction to occur. What does that mean? Let us consider this equation, that is 2NO gives N2 plus O2. For this reaction to occur, suppose we have the orientation like this. Okay, and then oxygen and oxygen and nitrogen in the right orientation. And then we will get the product N2 and O2. But if the orientation of nitrogen and oxygen is like this, no reaction will occur. And the second thing is the molecules must collide with enough kinetic energy to react. What is that means is they must meet or exceed the energy of activation. Or we will say that collision must be effective. So the frequency of these effective collisions determines the rate of that reaction. We can show the energy possessed by the particle as the reaction proceeds by this energy diagram. Molecules with enough energy will reach to the highest energy level here. So notice that in the example reactant here, carbon to nitrogen bond, that's the old bond in the reactant breaks, and the new bond, that is carbon to carbon bond, is formed in this example. So old bonds are breaking and the new bonds are forming. So how is that happening is the atoms in the molecule are reorganized at this highest energy level. So the organization of the atom at this highest energy state is called the transition state or the activated complex. So the energy needed to form this state, we call that as activation energy and represented by EA. Now let us see what happens when the temperature is increased. As you know, when the temperature is increased, the kinetic energy of the particle increases and the molecule speeds up and collide more frequently with a more energetic collision, right? And now only those particles represented by the area to the right here, right of the activation energy mark. This is the activation energy because energy is marked on the x-axis and number of particles or fraction of molecule that will take part in the reaction is marked on the y-axis. So we can see that only these particles on the right of this activation energy will react when they collide because that's the minimum energy required for the reaction. Only if that has this minimum energy can react effectively by effective collision, right? So the majority don't have enough energy. So what they will do, and they will simply bounce apart. So for the same amount of gas, if we are increasing the temperature from the lower temperature to higher temperature for the same number of particles in the reactant mixture, what happened? We can see that the more molecules, higher temperature, more molecules are energetic enough to achieve that activation energy. Thus, what happens? More molecules react and the overall reaction rate increases. So we can notice, you can notice that more molecules are to the right now, right of that activation energy now. And what will happen? The reaction rate will increase because we have more effective collision happening at higher temperature. So more molecules will be having that effective collision. So the reaction rate will increase. These effective collisions determines the rate of the reaction. So the mathematical representation for this rate of reaction and the temperature is developed by Arrhenius, and we call that one as Arrhenius equation, which is represented as K equal A e to the power negative EA divided by RT, where K is the rate constant and A is the number of effective collisions, and E is e to the power negative EA. That means EA is the activation energy and R is the gas constant and T is the temperature in Kelvin scale. In the same way, we can explain the effect of catalyst on the reaction rate. So what happens when you add a catalyst in the reaction mixture is catalyst increases the number of effective collision, and also what it will do, it will provide a reaction pathway which is very lower in activation energy. So in this example, we can see that enzyme is a catalyst. So without enzyme catalyst, the activation energy is here to the reactant energy, whereas with catalyst enzyme, the activation energy is very low from the blue peak here to the energy of the reactant. Compare the number of particles that will have effective collision and will be able to overcome the activation energy in presence of a catalyst can be represented in this energy diagram here. So in the top one, the number of collisions with a given energy, we can see that the blue shaded area, this is the activation energy here. Only the blue shaded area is the effective collision, the particles with effective collision. Whereas when you add a catalyst to that, the same number of particles we can see here, and we are adding the catalyst, what happens here is the activation energy, when you compare, you can see that activation energy is lower, and in this case it is higher here. This point is because the energy is increasing this way, this is higher activation energy, and here the lower activation energy. So more particle will have effective collision in a catalyzed reaction. This energy diagram also shows the effect of a catalyst, but only difference is in presence of catalyst we can see two peaks here. That means the reaction is taking place in two steps. So if the activation energy is lower, we can say that it is actually happening faster than the one with a higher peak. So this reaction is going to be slower and this reaction is going to be faster. That explains the mechanism of that reaction. So what is mechanism is, it's a series of steps, series of reaction happening, and kinetics gives us what happens, whereas the mechanism will tell us why it happens. So let's see the main points in the reaction mechanism. We will be using this vocabulary while explaining the mechanism. So the first one is molecularity. Molecularity means it will tell us how many molecules are involved in that step of mechanism. We can explain that one in detail with examples. And let us go ahead and see the next vocabulary, which is elementary reaction. Elementary reaction means reactions may occur all at once or through several discrete steps. So each step in a reaction, we call that one as elementary reaction, or we can just say elementary process. Next one is intermediates. Intermediates are made and used up. That means how can you identify is it will appear in the product side first and then it will reappear in the reactant side in the next elementary process. And what is a catalyst? Catalyst is nothing but it is used and regenerated. So that means it will appear in the reactant side of the elementary step and then we can see that same molecule or compound on the product side of that next elementary step. And then rate determining step, what is that means is the slowest step in that reaction mechanism is the rate determining step. So how fast it can go is determined by the slowest step. So let us see each one with examples. Here we can see several examples for the molecularity. So the first one we can say in the elementary reaction, reactant A gives product. We have only one reactant here. So we call that one as unimolecular. And the rate expression we can write rate equal K concentration A. And if we have two molecules that is reacting in an elementary reaction, we call that one as bimolecular. It is not necessary that they are the both reactants. They can be different reactants too. And still we will say bimolecular. That depends only on the number of reacting molecules. So we can write according to that, we can write the rate expression as well. I'm going to concentrate on the molecularity and elementary reaction. And if there are three molecules in the reactant side, we can say termolecular. Again, it's not necessary that we have to have the same molecule. We can have different molecules. So that is what is called molecularity. In this example, we have slow and fast step, and we can write the rate expression based on the slow step. So the slow step shows on the reactant side we have NO2 and F2. So we will just use those two in the rate expression. So we can write rate equal K, that is rate constant, concentration of NO2 times concentration of F2. We don't have any coefficient here, so we will just write like that. So in the case of mechanism, we are looking for the coefficient to put an exponent. Since I don't have any coefficient here, I will just leave it like that. So the first step is not involved in the rate determining step, so we don't have to worry about in writing the rate expression with the fast reaction. So for example, if we are asking to write the intermediate here, I can look for something is generated in the first step and something is used up in the second step. So we can say the intermediate in this case is F. That is the intermediate. Do we have any catalyst here? I don't see same thing on the left starting with and ending with. So I don't have any catalyst here. No catalyst. I have only intermediate. Let's see another example here. Nitrogen oxide is reduced by hydrogen to give water and nitrogen. So the equation is given 2H2 plus 2NO gives N2 plus 2H2O. So, and one possible mechanism to account for this reaction. So we have three elementary reactions here. The first one is 2NO gives N2O2, and the second elementary reaction or process is N2O2 plus H2 gives N2O plus H2O, and the third elementary step is N2O plus H2 gives N2 plus H2O. So the question is, what is the molecularity of each of these three steps? That means we have to find how many molecules are in the reactant side. I can see in the first one, two molecules. So we can call this one bimolecular. And the second one, we can see one N2O2 and one H2O2, but total two. So it's also going to be bimolecular. And the third one, we can see again two. So we can call that third step also bimolecular. And the next question is show that the sum of these elementary steps yield the net reaction. So this is our net reaction, and we have to add these three to prove that that equals the net reaction. So in that case, what we have to do is we have to see the same compound on both sides and cancel them out, just like we are adding algebraic equation. So I'm going to add that after cancelling. So I have N2O2 here, N2O2 here, and then I have N2O and N2O, and I don't see anything similar on both sides of the equation. So after that we can add on the left side I have 2NO left, and also I have hydrogen left, two of them, one from the second step and one from the third step. And on the right side, product side, I have two water molecule and one nitrogen. So I will just write N2 and 2H2O. So that is matching with our net equation or net reaction. And now try this question, pause it and check your answer in the next slide. Hope you have these answers.